Hello and welcome to the section 5.3 lecture video. So let's go ahead and get started by opening our notes to page 15. So we've been talking about this idea of the area under a curve, and what we're going to start relating it to is the idea of integrals that we looked at the end of chapter 4.7. And so what we're going to do today is define something called the definite integral. So let f of x be a function defined on a closed interval a comma b. Then we say that a number j is the definite integral of f over a comma b, and that j is the limit of the Riemann sums from k equals 1 to n of f of c sub k delta x sub k if the following condition is satisfied. Given any number epsilon greater than 0, there's a corresponding number delta greater than 0, such that for every partition of P from x sub 0 to x sub n of a comma b, with the norm of P being less than delta, and any choice c sub k in x sub k minus 1 to x sub k, we have the limit, the absolute value of the sum of f sub ck delta x k minus j is less than epsilon. So in other words, we're defining this using our limit notation. And then when this limit does exist, we say that j equals the limit as the partitions get smaller and smaller and smaller from k equals 1 to n of f sub c sub k is delta x sub k. And we have some notation for j that we're going to use. We can write j equals the integral symbol from the beginning of our interval a to b of our function f of x dx. So that's going to be our definite integral notation. So we can take limits and write them as definite integrals, and we can also take these definite integral symbols and write them as limits. So let's start out by taking the limits that we looked at in the last section and writing them as definite integrals. So if I wanted to take this limit and write it as a definite integral, I start by writing the integral symbol and what the partition is over. So in this case, we're going to go from 1 to 4. And then we simply have to write in what the function is. Well, in this case, the function is 1 over ck, so 1 over the x value, right? C sub k is the x value. So that would just be 1 over x dx. Okay? And that's all there really is to that. So the next one, we write the integral symbol. Our partition is from 0 to 1, so at the bottom of the integral symbol, we put the beginning of our integral, which is 0, our partition, which is 0 here, and then where we end, and then we write the square root of 4 minus x squared. We simply take the expression that's inside the sum and replace c sub k with x. And then we finish it off by writing dx. And the dx is simply telling us what variable we're taking the integral with respect to. Because when we get to Calc 3 and you start doing, or even later in chapters here where we're having more than one variable, we need to know which variable is the one we're actually dealing with. Okay, so at this point, go ahead and pause the video for a moment and try writing the last two limits as using this definite integral notation. Okay, so now that you've had a chance to try this, let's go and go these last two together. So in the second to last one, our integral goes from -1 to 0. So -1 on the bottom, 0 on top. And our expression is 2x cubed. And then for the last one, we go from 0 to pi over 4. And our, sorry, I forgot a dx here. And our our function is tangent of x, dx. Okay, and so that's all there is to going between these two notations. So now we have a lot of definite integral rules that are really important. So the first one says, if a function f is continuous over an interval a comma b, or if f has at most a finitely many jump continuities, then the definite integral a comma b of f of x dx exists, and f is integrable over a comma b. Okay, so some different rules satisfied by definite integrals. So first of all, if you want to flip a and b, so notice here it goes b to a, here it goes a to b, that's simply going to be opposites of each other. So if we flip the order of the interval, we simply get the opposite integral. Also, if our integral starts and stops at the same place, then that has no width, and therefore there is no area. Because if the way we find area, right, is length times width. If width is 0, then the area is 0 no matter how high it is. Remember, these are similar to the limits of sums. These are equal to the limits of sums. So if we have a constant multiple, we can just bring it out in front, just like we can with limits and with sums. If we're doing the sum or difference of two functions inside an integral, we can break that apart back into two separate integrals, just like we could with sums. And if we, just like with sums, when we could subtract two sums to get a smaller one, if we want to add two integrals where one ends at b and the other one starts at b, then those two added together would simply be the function from a to c. So a to b, b to c is the same thing as a to c. The min-max identity, max-min identity says if f has a maximum value, max f, and a minimum value, min f, on a comma b, then the minimum of f times a minus b is less than or equal to the integral a comma b f of x dx, which is less than or equal to the maximum value of f times b minus a. So the idea here is simply that if I had, if this is, let's say my function looked like this. So I have a min and a max. So over here is a, and over here is b. Okay, so I have a minimum and I have a maximum. The total area of under this curve is going to be somewhere between the area if I took the height at a times, so if I took the minimum, which is this height here, times the width. So that would give me this area. And if I took the max times the width, the actual area is going to be somewhere between those two values, which should make some sense, right? This has a rectangle that's too big. This is the bottom is a rectangle that's too small, and so the actual area is somewhere in between those two values. And then another concept here is called domination. So if f of x is greater than or equal to g of x on a comma b, then the integral of f of x dx is greater than or equal to, sorry, this is a typo, the integral of g of x dx. So if your function is always larger, if one function is always larger than the other one or equal to, then its integral will always be larger than or equal to. So therefore, if f of x dx is, if f of x is always greater than or equal to 0, the integral of f of x dx will also be greater than or equal to 0. Okay, so now what we can do is play around a little bit with these rules without actually knowing the values of functions. So, for example, here they're telling us that what the value of h of r dr from -1 to 1 is and what it is from -1 to 3. And so then we can try and find some values of different functions here using these rules. So if you look at the first one, we want to know the area from the definite integral from 1 to 3 of h of r dr. Well, one of the rules we have is that these things can be added together. So, for example, if I were to add this one, -1 to 1 h of r dr plus 1 to 3 h of r dr, that should equal -1 to 3 h of r dr. So here I'm just using the additivity rule, number 5, by saying that if I want to go from -1 to 3, well, I could do that in two pieces, and those two should add together. And we know what h of r dr is. It's 0 from -1 to 1. I don't know what it is from 1 to 3, so I'll leave that alone. And I do know what it is from -1 to 3, which is 6. Add these two together, and we just get h of r dr from 1 to 3 is 6. Okay, so that's the idea, using that rule. Another really important thing for these is the variable we're plugging in does not necessarily matter in these examples. So negative 3 to 1 h of u du is going to be equal to negative 3 to 1 h of r dr. Right? I can just replace the u's with r's. And then I can get rid of the negative by flipping this over. So this would be 1 to 3 h of r dr. And we already know from the previous problem that that's 6. Okay, so that's the idea we're looking at here. So what would f of x dx of 5 from 1 to 2, what would f of u du be? Well, that would just be 5, right? Because it does not matter that I'm using u's instead of x's. Okay, those are still having the same value. Here, I have a constant multiple, so I can bring that out in front. And then we can replace f of z dz from 1 to 2 with 5 because we know that's what it's equal to. This would be the square root of 3 times 5, or 5 root 3. And then the last one, notice that the endpoints are backwards. So that's going to be if I want to flip them correctly, I just take the opposite from 1 to 2 of f of t dt. And so then that would be the opposite of 5. That's what I get for that. Okay, so at this point, why don't you go and pause the video and try doing these ones on page number 17. And then when you're ready, we'll get started again. Hit play and we'll go over them together. Okay, so the first one here, we know the derivative. We're trying to find the derivative of 1 to 7. We know the derivatives from 1 to 9 and 7 to 9. So we can use the same rule we used on the last page, and we can do 1 to 7 of f of x dx plus 7 to 9 f of x dx has to equal 1 to 9 f of x dx. And then we can substitute in the values we know. We don't know 1 to 7. We do know that the derivative for the integral from 7 to 9 of f of x dx is equal to 5 from right there. And we know that from 1 to 9, it's equal to negative 1. Subtract 5 from both sides, and we get that the integral from 1 to 7 of f of x dx equals negative 6. The second one here is asking us to use several different rules from the previous page, the constant multiple rule and the difference rule. So I could rewrite this function, this integral, as 2 times the integral from 7 to 9 of f of x dx minus 3 times the integral from 7 to 9 of h of x dx. So I use the difference rule to break it in 2, and then I use the constant multiple rule to bring the 2 and the 3 out in front of their integrals. And so now I know the value of these two integrals from up here. From 7 to 9 of f of x is 5. From 7 to 9 of h of x is 4. So this would be 2 times 5 minus 3 times 4. So that's 10 minus 12, which is negative 2. Okay, so that's the idea. So here we have a constant multiple of negative 2. Bring that out in front. The integral from 1 to 9 of f of x dx is negative 1, so this will be negative 2 times negative 1, which is 2. This one here, just use the sum rule, right? So the integral from 7 to 9 of f of x dx plus the integral from 7 to 9 of h of x dx, and we can substitute. So f of x dx from 7 to 9 equals 5. The integral of h of x dx from 7 to 9 is 4. So this is 5 plus 4, which is 9. The second to last one, the problem is that our endpoints are backwards. So we can change that by doing the opposite of the integral from 1 to 9 f of x dx. And then we can just substitute. So substitute in negative 1. So this is negative negative 1, which is positive 1. And then the last one here, similar idea, right? I have backwards integral, so we can fix that first by making this a negative 7 to 9 of h of x minus f of x dx. And now we can use the difference rule. And so this is negative 7 to 9 of h of x dx minus 7 to 9 of f of x dx. And the negative still applies to the whole thing, which is why I added the brackets. And now we can substitute. So h of x over that interval is 4. F of x over this interval is 5. So this is negative 1, which is 1. So those last two are actually equal to one another. Okay, so that's just using some of the rules. Now what we're going to build into is the idea of actually finding areas with these things. So the next one definition here is if y equals f of x is non-negative and integrable over a closed interval a minus b, then the area under the curve of f of x over a of b is simply the integral from f to b. So notice there's a couple of things that are important here. F of x has to be non-negative for this to be the area. Okay, so let's go and see if, so it says graph the integrands and use the known area formulas to evaluate these integrals. So one option we have here is to do this with sums and differences, but we can also, with some of these graphs, use areas we know. So like, for example, if I graph this first one, so let's go to our graphing calculator here. And I'm going to go to graphing, and I want to graph 1 minus the absolute value of x. Okay, and I want to do that over the integral. So now I can click and hold on the colored circle, and it'll bring up this menu, and I want to set the domain to be my bounds, which are -1 to 1. Whoops, sorry, but -1 to 1. And so if we look at this graph, what we can see, and actually if I wanted to, we could copy and paste this into our notes here. So if I plug this into my problem, so this is for this first one. Okay, so what we want to notice is that this makes a shape that we recognize. And the shape that we should recognize is the fact that this, here's the x-axis, so the area under the curve is a triangle. So we can use the known area we know about this one, which is what's the area of a triangle? Well, if we look at this triangle, it goes from -1 to 1, so that means the base is 2, and it goes from 0 up to 1, so the height is 1, and the area of a triangle is 1/2 base times height. So this would be 1/2 times 2 times 1, which is an area of 1. Okay, so that's one way we can do these, is simply by using the area formulas we know. So let's look at another one. So if I graph the second one here, so the second one is 1 plus the square root of 1 minus x squared. Okay, and if we look at this one, what we get is we get a semicircle that's above the x-axis. So if I do the same thing I did here, I'm going to copy this into my notes. Okay, so I'll copy the graph in here. Oops. Okay, so if you look at this graph, and I'm doing the area above the x-axis, so here I'll go and add the x-axis in here a little darker. So the x-axis is down here. We want to find the area above that under the curve. So the curve is up here. This is the curve, right? is the semicircle. So we want to add in this area at the bottom. And so what we actually get is two different shapes we know the area of, right? If I draw a line there at the bottom of the circle, I have half a circle and I have a rectangle. So to find that area, I just want to add those two together. So the base here is 2, right? So for this one, this is 2 by 1. So that area, base times height, is just 2 times 1, which is 2. And then the area of the top has a radius of 1, and the area of a semicircle would be 1/2 pi r squared. So in this case, that'd be area equals 1/2 pi 1 squared. And so the area of this piece is just going to be pi over 2. Add those two together, and you get an area of 2 plus pi over 2. Okay? And so that's the idea. Okay, so what I'd like you all to do at this point is pause the video for a moment and try graphing these other two and finding their areas in the regions given. Okay, so now that you've given those a try, let's go through them together. So if I graph the first one, so the first one is negative 2x plus 4. And I want to graph that from set my domain to be 1/2 to 3/2. Okay, and so our graph looks something like this. Okay, and let's go ahead and just graph the second one too while we're at it. So the square root of 16 minus x squared from -4 to 0. So the square root of 16 minus x squared from -4 to 0. Okay, and we can zoom out on that a little bit. And so here's that graph. Okay, so let's go ahead and insert those. I'll go ahead and insert those into my notes, and then we'll find their areas. Okay, so if we start with the one on the left here, notice that we want to, like we had to do with the circle here, we need to connect that down to the x-axis. So take your endpoints, 1/2 and 3/2, and connect those down. And now you can break this into two shapes, right? I've got a triangle and I've got a square, or a rectangle. It's a square and a rectangle. So the base of the square is 1 because it goes from 1/2 to 1.5. So that's 1. The height is 1. So the area of this rectangle is just going to be 1 times 1, which is 1. And up here we're doing the area of a triangle. The base of this triangle is 1 because it's the same as the base of the square below it. And the height is 2 because it goes from 1 to 3. So the area of a triangle is 1/2 base times height. So that's 1/2 1 times 2, which is just 1. Add those two together. And so we get an area of 2 for that triangle. And then for the circle, for the second one, what we get is a quarter of a circle, right? So the radius of this, so the piece we're looking at here is this piece, right, which is a quarter of a circle. So the radius of that is 4, and the area of a quarter of a circle is just 1/4 times pi r squared. So that's 1/4 pi times 4 squared. 1/4 times 4 squared, well, that's 1/4 times 16, which is just 4. So this would be 4 pi. Okay, so that's one way to find the area under the curve, is if it's a circle or a triangle or a square or a rectangle, something we already know how to find the area of, you can just use the formula. However, if we don't know that, we're going to need to go a little bit further. So, if we go to this page, we can talk about that. Okay, so what we want to try and do is we want to try and build up an idea of what this area is going to look like using limits. So, what we're looking at here is it says compute 0 to b of x dx and find the area A under y equals x over the interval 0 to b. Okay, so what we start out with is we could draw some axes so we can see what's happening here. Okay. And then what we get is the line y equals x, which looks like this. And we want to go to b. Okay. And so now we can use what we were just talking about to find the area under the curve for that. So if I look at this ordered pair up here, because y is the same as x, is going to be b comma b. Okay. And this ordered pair is 0 comma 0. So the shape here that I'm trying to find the area under the curve for is a triangle. And we already know from the last page that it's 1/2 base times height. So here the base is going to be b, right? From 0 to b is b. And this will also be b, right? Because I go from 0 up to b. And so the area here is going to be 1/2 base times base, which is 1/2 b squared. So the integral from 0 to b of x dx is just b squared over 2. Okay, and now an interesting thing to notice here is that this b squared over 2 may actually look fairly familiar to you, because if we talked about the indefinite integral of x, that was we added one to the exponent and then divided by that new exponent. So that would be for x, would be x to the second power divided by 2. And then if I plugged b in for x, I would get b squared over 2. And so that's kind of the idea we're looking for here. So we can give you a couple of other rules. And this idea that if I go back, let me actually write that down, right? One of the things from section 4.7 is that the definite integral of x dx was x squared over 2, and the definite integral and some other useful ones are the definite integral of a constant was, plus a constant c. The definite integral of c was cx plus a capital C constant. And then the indefinite integral of x squared dx was x cubed plus 3 over c. Now, if we put that together, along with the idea of taking the function from from each side of the endpoint, what we get is these ideas down here. That the way we can find definite integrals is by finding the indefinite integral using the rules we know, and then finding its value at each endpoint and subtracting. Okay, so that's what these examples here. So for an actual example of what this would look like, if I wanted to find the this should be an equals in the third one here. If I wanted to find the definite integral from 0 to 0.3 of s squared ds, what I would basically do is start out by finding s squared's indefinite integral, which is s cubed over 3, or using this formula here, and then we simply plug in the endpoints, and we take the higher endpoint minus the lower. So this would be 0.3 squared over 3 minus 0 squared over 3. And then we can plug that in our calculator if we want. Or we can do it by hand. 0.3 squared is 0.09 over 3 minus 0 over 3. So this is going to end up being 0.003. Okay, so for now what we're doing is we're just recognizing which formula of these three to use. So these three formulas, maybe also some of our rules from earlier in the section, and then simplifying. So like for this one, 1 to root 3 of x dx, I noticed that that's the first formula. Right, so I'm going to use this one up here. So that would be the square root of 3 squared over 2 minus 1 squared over 2. So that would be 3 halves minus 1 half. And then we can simplify. 3 halves minus 1 half is 2 over 2, which is 1. Okay, and the last one, here I have an r, so that means I'm using this first formula again, right? R dr. So that would be 5 root 2 squared over 2 minus square root of 2 squared over 2. 5 root 2 squared is 5 squared, 25, times root 2 squared, which is 2 over 2, minus 2 over 2. Simplify, and you get 25 minus 1, which equals 24. Okay, so that's the idea. So go ahead and flip over to the next page. Actually, let's go ahead and talk about these a little bit more together. So now we can use all of our rules together and simplify some of these, and then I'll have you all try. We'll do a couple together, and then I'll have you all try some. So I can use my new 3 rules on the last page for a constant, x, and x squared inside a definite integral, along with my sum and different rules and my constant multiple rule and things like that. So if we did this one, the first thing we would want to do is break this apart into 2 separate integrals. So this would become 0 to root 2 of t dt minus 0 to root 2 times the square root of 2 dt. And now I can use the formulas from this page. So for the first one, I've got t to the first power, so that's the first formula. And then I have a constant, so that's the second formula. So for this one, it's going to be the square root of 2 squared over 2 minus the square 0 squared over 2 minus the square root of 2 times b minus a. So the square root of 2 minus 0. So now we simplify. So square root of 2 is 2. Squared is 2 over 2 minus 0 over 2 minus root 2 times root 2, which is 2. So this would be 1 minus 0 minus 2, which is negative 1. Okay, so that's the idea. That's what we're trying to do here. So if we look at the second one here, the first thing you want to notice, well, there's a couple things we need to notice here. One is this is upside down. We go from A is not less than B. So we want to flip this over. And so this would be 0 to 1, the opposite of 0, the integral from 0 to 1 of 3x squared plus x minus 5 dx. And now we can break it apart using our rules. So this would be negative stays all the way out in front. The integral from 0 to 3 times the integral from 0 to 1 of x squared plus the integral from 0 to 1 of x minus the integral from 0 to 1 of 5. And I forgot to put dx's on all these. And then close that parenthesis because we're going to take the opposite of whatever we get. So now we can use our rules. So the rules for x squared is x cubed over 3. So b of x cubed over 3 minus a cubed over 3. So this would be 1 to the third power over 3 minus 0 to the third power over 3. Plus the rule for x is x squared over 2. So this would be 1 squared over 2 minus 0 squared over 2. And then for a constant, you simply take the, minus. You take the constant times the width of the interval. Okay, now we can simplify each one of those. So this is going to be the opposite of 3 times 1/3 plus 1/2 minus 5. And then we just simplify. So that's 1 plus 1/2 minus 5. So 1 plus 1/2 minus 5 is negative 7/2, and negative 7/2 is just 7/2. So the area under that curve would be 7/2. Okay, so at this point, go and pause the video for a second and try these other two. Okay, so now that you've had a chance to try these, let's go through them together. So the first one, use the constant multiple rule to bring the x out in front. And now we have the integral of x squared, so that's b squared over 2, of x, so that's b squared over 2 minus a squared over 2. So this would be 5 times b is 2, so 2 squared over 2 minus a, which is 0 squared over 2. So that's 5 times 4/2 minus 0/2, which is 5 times 2 minus 0, which is 10. And then for the second one, we need to do the same idea that we started out with for the second one here, which is we need to take the opposite of the whole thing to get the integral in the right order. Now I can break it into pieces. So this is the opposite of dz, there still. 0 to 3, 2 times the integral of 0 to 3 of z dz minus the integral from 0 to 3 of 3 dz. And now we can do those rules. So the integral of z is b squared over 2 minus a squared over 2. So b is 3, so 3 squared over 2 minus 0 squared over 2. And for a constant, we just take the constant times the size of the integral. So negative 3 times 3 minus 0. And now we simplify. So this is negative times 2 times 9/2. So square the 3 and we get 9/2 minus 3 times 3. So that's 9 minus 9. So this ends up being the opposite of 0, which is 0. Okay, so that's the value of that integral. Okay. Now, the next thing we need to talk about is, well, what about more complicated ones here? What if we, so far the only way we know how to do calculus with these is by using the limit of a Riemann sum. Well, we can do that here too with these. So to find the limit, to rewrite these as a limit of a Riemann sum with equal width subintervals, we can use basically use the idea we were using at the end of the last section. So if I want to find the integral from 0 to -1, I can just plug all these values into here. So for example, in this first case here, we can rewrite these. So our limit with this is we really just need to know what A, B, and F are, right? Because those are the variables here. A, B, the constants, and whatever F is. So our function here, f of x, is x minus x squared, and our A is where our interval starts, which is -1, and our B is 0. And so we can plug those in. So this would be the limit as n approaches infinity of the sum from k equals 1 to n of f of a plus k minus b over a n and so on. So we plug a plus k times b minus a over n into the function. So that would be a, which is negative 1, plus 0 minus k times 0 minus negative 1 over n, minus the same thing squared. So negative 1 plus k times 0 minus negative 1 over n squared, times b minus a over n. So 0 minus negative 1 over n. Okay. And so then we could find the value of the definite integral by doing that limit, which is something we talked about in the last section. Okay, so we're not going to do it here. We just need to be able to write it this way, and then you guys should be able to do that. So I'll simplify it a little bit, but this is the limit as n goes to infinity from the sum of k equals 1 to n of negative 1 plus k over n minus negative 1 plus k over n squared times 1 over n. Now, the reason I'm not going to go through doing that too is because we actually have an easier way to do this definite integral, as we saw on the last page. So I'll write that out here, and that's how you could do most of the ones on this page. In fact, that's how you could do all of these. You just have to take some of them a step further. So like, for example, here I could use the rules that I talked about on the last page, and this would be negative 1 to 0 of x minus dx minus negative 1 to 0 of x squared dx. And then we could use the rules that we talked about. So this would be b squared over 2 minus a squared over 2 minus now we x squared, so that's going to be b cubed over 3 minus a cubed over 3, and then just simplify, okay, from there to get the answer. So in this case, this would be negative 1/2 minus negative 1/3. Minus, that's going to end up being positive 1/3, so minus 1/3, which is negative 5/6. And so this is a much easier way to do this than using the limits. And that's what we're going to talk about more, how to do this inside the box in the next section with more complicated functions. We're going to take this further and further. Now, if you look at, say, the last one here, which we haven't talked about yet, once again, you could write all these as Riemann sums if they ask you to do that on the homework, but to find the actual value, it's easier to do it the other way. We haven't talked about x cubed yet, but we've seen that the pattern is to do the indefinite, is to use the indefinite integral. So what is the indefinite integral of x cubed dx? Well, we did that in last chapter, right? You add 1 to the exponent and then divide by that number. So this would be x to the 4th over 4. And so to do this indefinite integral, I would just plug in b minus a into this function. So it would be 1 to the 4th over 4 minus negative 1 to the 4th over 4. And when we do that, we get 1/4 minus 1/4, which is 0. Okay, so that's the idea. Now, the last thing on here is the idea of average value of a function, which we touched on briefly in 5.1, finding an approximation for this using rectangles. But now we can do it exactly using this idea of definite integrals. So if f is integrable over an interval, we can find its average value on that function by also called its mean, by using the formula 1 over a minus b times the integral from f of x dx. Okay, so minus its definite integral. So for example, if I want to find the average value of this first function, that's going to be 1 over b minus a, so 1 minus negative 2, times the integral from negative 2 to 1 of t squared minus t dt. And now we can just use the rules we've talked about in the previous pages to find this definite integral. Okay, so that's going to be 1 over 3 times, I break this into two pieces, right? The definite integral from negative 2 to 1 of t squared minus the definite integral dt minus the definite integral from negative 2 to 1 of t dt. And then use the rules. So this would be 1/3 times b to the third over 3 minus a to the third over 3 minus, and then I do the second definite integral. And so that's a squared over 2 minus b squared over 2 minus a squared over 2. Okay. And then we simplify. So this would be 1/3 times 1/3 minus 8/3, negative 8/3, minus 1/2 minus 4/2. So that's 1/3 times 9/3 minus negative 3/2. So that's 1/3 times so 9/3 minus negative 3/2 is 3 plus 3/2. So that's 9/2. Multiply those together and you get 1/3 times 9/2 is 3/2. So the average value of this function over the interval would be 3/2. And so that's the idea. So at this point, if you want to, you can pause the video momentarily and try these last two. And then once you're ready, you can hit play and we'll go through them together. Okay, so now that you've tried these, let's go through them. So the next one, same idea as what we did above. So I take 1 over the interval, so 1 over 3 minus 0, times the definite integral from 0 to 3 of negative x squared over 2 dx. Okay. Now, so that's equal to 1 over 3, and I can bring out the constant, which is negative 1/2, so times negative 1/2, times the integral from 0 to 3 of x squared dx. And now we can use the rule. So this would be 1/3 times negative 1/2 is negative 1/6 times x squared. So that means I'm going to do b cubed over 3. So that would be 3 cubed over 3 minus a cubed over 3. So 0 cubed over 3. So this is negative 1/6 times 27 over 3 minus 0 over 3. So negative 1/6 times 27 over 3, which is when we multiply those together, we get negative 3/2. Okay, and then the last one, same idea. So multiply the width of the region, so 1 over 1 minus 0 times the the integral, the definite integral from 0 to 1 of 3x squared minus 3 dx. So that's 1 times, I have to break this into pieces, so 3 times the integral from 0 to 1 of x squared minus the integral from 0 to 1 dx, minus the integral of 3 dx. So the 1 out in front just goes away, and I can write out these integrals. So this is going to be 3 times, it's x squared, so that means I'm going to do b cubed over 3. So 1 cubed over 3 minus a cubed over 3 minus, this is a constant, so I just take the constant times the width of the region. So 3 times 1 minus 0. So this is 3 times 1/3 minus 3. So that's 1 minus 3, or -2. Okay, and that is it for section 5.4. So in section 5.4, we're going to use the fundamental theorem of calculus to define this idea of finding definite integrals and make it a lot easier. But that's it for now. Don't forget to do your homework. And don't forget, if you ever have questions or concerns, you can always call, text, or email me.